Good afternoon, one and all. Today, we are going to see about the systematic short circuit computation, that is Zbus in phase frame. So, how the short circuit is being systematic short circuit computation. So, how we are going to do like that. Generally, fault analysis using the Zbus matrix. So the algorithm goes like this. In large network, the network reduction techniques is not applicable. Say, for example, if you take some two bus system or three bus system, the network reduction is possible. Up to 5 bus system, network reduction is possible because already we have seen the many classes how to reduce the 4 bus system, like say, for example, the matrix size is 4x4 matrix. So that 4x4 matrix can be reduced to 3x3 matrix based on your bus system and the shortcut techniques by using cross reduction method and some shortcut techniques also be already we have seen many classes solved many problems also on that. So here you see the network reduction is not possible in the large network. Say, for example, it is a 40-bus system. There, you can't reduce the network to, say, for example, 41 cross 41 matrix will be there. That you can reduce to 40 cross 40 matrix. It is not possible, not applicable and also not possible. Calculation is very complex. So what we are doing is by utilizing the elements of bus impedance matrix, fault currents, bus voltage during the fault can be easily calculated. What we are doing is by using the elements of bus impedance matrix, fault current and bus voltage during the fault. Bus voltage during that particular fault can be easily calculated to involve digital computer in the short circuit computation. As we discussed earlier, we can easily program those short circuit analysis in the computer programming. That you can solve the problem. It is necessary to develop a systematic general computation procedures. It is necessary to develop a systematic. So some systematic computational procedures should be there, should be followed for all, so that you can easily solve this kind of short circuit for large networks in digital computers. Consider a typical bus of N-bus system. Say, for example, we are considering a N-bus system like this. Say, for example, this is the generator 1 having the impedance of XD1 double dash. XD1 double dash already we have seen subtransient reactions, okay, transient reactants like that we already seen in our previous classes. So here XD1 dash and also the generator 2 has XT2 double dash that is connected to a transmission system and it is connected to, say, for example, bus 1 up to bus N. This generator size is of more and it is connected to a some nth bus system. We can't, so N means you can fill anything, 40 bus system, 118 bus system, 200 bus system. It depends on the practical system. You can fill the number of buses as N, anything you want. So that is the N bus system as shown in the figure. The system is assumed to be operated under the balanced condition and a per phase circuit model is used. So it is assumed to be operated under the balanced condition and also per phase circuit model is used. So there are some predefined steps or algorithm, we can call it as algorithm for solving this N-bus system, short circuit analysis of a N-bus system. First step, draw the prefault per phase network, that is positive sequence network. So you know in power system, positive sequence, negative sequence, and zero sequence networks are there. So here, what we are doing is we are drawing the prefault per phase network analysis by using the positive sequence network. So in this, each machine is represented by a constant voltage source behind a proper reactance. So each machine, say for example, this is a generator 1, power voltage in the generator 1 is EG1, voltage in the generator 2 is EG2, and having some reactance of xt1 double dash here, xt2 double dash as shown in this figure. So I think, yeah, in this figure, it is clearly mentioned we are now that reactance, this system diagram, bus system diagram, what we are doing is we are converting that into your equivalent reactance diagram. That is generator 1 having the voltage, flat start voltage as 1 at the angle of 0. So why we are going for flat start voltages? It is in per unit. So any voltage source, say for example, that generator size is 25 kilovolt or 11 kilovolt. So that you can convert into per unit, means definitely it will come 1 per unit only. So here the voltage value here is 1 at the angle of 0. That is 1 plus J0. So if you want to convert that into exact you need to convert, you need to multiply with that base values and you can get that voltage. So say for example 25 kilovolt or 11 kilovolt, whatever the generator size might be. So here you need to convert that into reactance diagram, and we are drawing this. That is what's told here. Transmission line reactants are expressed in per unit on a common base ME. So on a common base ME, so if you see some problems, already solved problems of ours. So what we did is we have taken the base MBA as some 10 MVA or 1 MVA. So based on the problem. So sometimes in the problem itself they mentioned take the base MBA as sometimes they will not mention. We need to choose from that generator value. That is a base MBA. We can take it as 10 MBA or 1 MBA based on the problems. So this is the pre-fault per phase network that already we have seen. And here you see having the here the fault is happening. Here is the fault is happening. That particular fault is happening here at the bus number Q. Okay, so having the fault impedance of ZF and the voltage between this bus and to the ground is VQ 0. So that is VQ naught. VQ naught, that is the initial value of the voltage where the fault is occurring. So let us assume three-phase fault occurs at the bus number Q through the fault impedance Z. So you might have come across a doubt how three-phase fault you are telling like a three-phase fault is occurring, but this is a single line diagram. So what we need to do is if you convert that this single line diagram into actual bus system diagram, so there the three-phase occurs. So there the calculation of a positive sequence, negative sequence, and zero sequence is possible. Say for example, if the fault, okay, in the fault analysis, say for example, negative sequence current is happening in that particular line means. So what we need to do? So we need to take that negative sequence like fault current into the account, and we need to solve the problem. So already that thing you already studied in detail in your previous classes. So here let us assume a three-phase fault occurs at the bus number Q. So Qth bus throughout the fault impedance Z. So that is happening. So pre-fault bus voltage. Pre-fault bus voltage, it is obtained from the power flow solution. Power flow solution, already we have seen many power flow solution how to solve. So here V bus naught is equal to V1 naught up to VQ naught. That is the voltage at the first bus is V1 naught, and the voltage at the qth bus is VQ naught, and the voltage at the nth bus is Vn naught. That is initial values. So this is the initial bus voltage. B bus naught. A good approximation to represent the load by constant impedance evaluated at the pre-fault bus voltage. That is ZIL. ZIL is equal to VI naught the whole square divided by this SL star. SL star is nothing but apparent power. So star, you know, that is the phase angle is negative. Okay, phase angle is negative. So that is the ZIL is equal to VI naught the whole square divided by SL star. This is the step number 1. That is step number 1 is we need to draw the prefault per phase network. That is positive sequence network. And also here you're calculating the initial buzzer voltage and as well as the constant impedance also that we are calculating here. So what is the step number 2 is obtain the Zbus matrix using the bus building algorithm. This bus building algorithm is detailedly we explained in our previous classes. So that class also possible I can give in the comment section. This also in the description I can give you. So this also you can watch. This is how to formulate this Zbus matrix by using that bus building algorithm. So that is having some 5 steps, steps, and we have solved many problems on the bus building algorithm also. So possibly I will give all this recorded links in the description. You can watch it later. So here to obtain the Zbus matrix by using the bus building algorithm and also equivalent circuit also here we need to draw. So after that, that is reactance with all the reactants. So the last class also we have seen whatever the bus system is there, fault analysis we have seen. That class also one problem we solved. So that also I will give in the link so that you can watch. So first of all, what you need to do is you need to calculate for a bus system is given. Say, for example, generator is there, some transformer is there, transmission line is there, another one transformer is there, another one bus is there, another one some lines is there, overhead lines is there. So everything you need to convert into reactants. So definitely some equipments. What are all the equipments connected at that particular system, connected on the particular system or taken system having some impedance. So that impedance we are taking into account. So that impedance we are calculating. So that also I have explained in the previous classes. That also you can watch. So what we are doing is we are converting that into reactance diagram. So here you see 2 generators, as I already explained, 2 generators are there. So that we are converting into per unit, that is 1 at the angle of 0 degree. And also here the terminals also we need to mention like positive and negative terminals. The sequence also we have to mention. So assume one node as a reference node, So any node you can take as a reference node and start circuiting all the voltage sources. Determine the bus Zbus by using the step-by-step bus building algorithm. The bus building algorithm I've already explained you. Next, step number 3, obtain the fault current. How to obtain the fault current is the same thing by using the Thevenin's theorem. So converting all the voltage source into single voltage source. So there may be many voltage source that into single voltage source, that is E Thevenin, and with that phase sequence that also you need to mention. And also all the impedance, that also what we are doing is we are converting all the impedance into that one impedance, that is Z Thevenin. One impedance that is connected, that impedance will be connected in series with that voltage, that is Thevenin voltage, and assume the fault is happening here. Assume the fault is happening here and having the fault current as IF and having the impedance, fault impedance as ZF. This is the qth bus. Qth bus means here only qth bus only that fault is happening as per our single line diagram. As per our single line diagram, here in the bus number Q only this fault is happening. So here we are mentioned as Q. Now, the changes in the network voltage caused by the added voltage VQ naught with all other sources are short circuited by representing all components and loads by appropriate impedance. That is, all the impedance we are converting into appropriate impedance, and we obtain the Thevenin's theorem by using how to calculate the fault current IF is equal to VQ naught. That is whatever the equivalent voltage equivalent voltage. Here it is mentioned as VQ naught, that is initial value VQ naught divided by this impedance. Impedance are connected with the sum of this all the impedance. That is only one Thevenin impedance is there. Here assuming that fault is happening in the this particular qth bus. So here the fault impedance also adding. So here we are adding ZQQ plus ZM. So I is equal to V by Z. That formula, basic formula. So here we are adding the this fault impedance and as well as the Thevenin impedance also here. So what is ZQQ? ZQQ is the diagonal element of the Zbus matrix. Diagonal element of the Zbus matrix. And ZF, you know, fault impedance that you know. Next, step number 4. The step number 4, obtain the Thevenin's network by inserting the Thevenin's voltage source VQ naught in series with ZF and compute the change in the bus voltage using the network equation. So what we are doing is we are obtain the Thevenin's network by inserting VQ naught. VQ naught here we are inserting the VQ naught here itself. In the qth bus, we are inserting the Thevenin's equivalent circuit having the polarity also we are mentioning positive here and negative here in series with the ZF, and compute the change in the bus voltage by using the network equation. So what is the current entering every bus in is 0. The current entering every bus is 0 except the fault bus. So fault bus having some current will be there. So I1 is equal to I2 is equal to up to IN is equal to 0 except IQ, because IQ only having that fault. So IQ is equal to minus IF, because since the fault current is leaving the bus Q. So assume the fault current is happening here and the fault current is leaving the bus Q. So here we are taking IQ is equal to minus IF. So what is I bus? So I bus, I bus is equal to I1, I2 up to IQ and up to IN. So because in the I bus, we are having the N buses and N currents, and assume that we have assumed one more bus also, that is qth bus also. In the qth bus, the fault is happening. So IQ also taken into the account. So here, substitute I1 is equal to 0, I2 is equal to 0, and IQ is equal to minus IF, because already we calculated IQ is equal to minus IF and IN is equal to 0. So I bus fault is equal to Y into change in the bus voltage, change in the bus voltage. So here we are solving for the del V, this change in the bus, del V bus is equal to Z bus into I bus. So how Z bus comes? So it is nothing but Y inverse. Okay, Y inverse. Say for example, if you are taking this del V bus outside, so this Y bus will come here. That is in the downwards. That is 1 by Y bus. So 1 by Y bus is equal to Z bus. Okay, so either Z bus into I bus. So that is what here. Z bus equal to Y bus inverse. Next, change in the bus voltage. Change in the bus voltage del V1, del V2 up to del VQ up to del V1 is equal to. So this impedance. So Z bus impedance already we have seen Z11, Z12 up to Z1N, Z21, Z22 up to Z2N, ZQ1, ZQ2, ZQQ up to ZQN, ZN1, ZN2 up to ZNQ up to ZNN. So that into this I bus fault. Okay, I bus fault is nothing but here. Why we are taking 0 here, 0, 0 minus IF 0. Already we calculated I bus is equal to 0, 0 minus of IF up to 0. Already we have calculated, just to use here we are substituting. This is the step number 4. That is, we are calculating that change in the bus voltage. Next, step number 5. What is step number 5? Post-fault bus voltages. Post-fault bus voltage. Post-fault bus voltages are obtained by superposition of the pre-fault bus voltages and the change in the bus voltages. So here, what we are doing is the system is complex. As I said, system is complex. So we can't solve. We can't find out the say, for example, exact change in the because and also the whatever the fault is happening, that will change the phase angle, phase sequence, and as well as the current. Okay, and also if the phase sequence is changing, it automatically changing the frequency, and also if frequency changes, our entire system will collapse. Okay, the frequency has to be maintained constant. Then only because all the equipments it is designed for only 50 hertz. So if due to some faults, if the frequency is more, instead of 50 hertz, the frequency is 60 hertz in the system, or instead of 60 hertz in the foreign countries, there is some 70 hertz in the system. So entire whatever the equipments connected in the particular system or particular bus, okay, loads connected at the particular bus system, entire equipments will get damaged and collapse. Okay, misbehave. Okay, say for example, if the frequency gets changed, say for example, if you are using a trimmer, you are using a trimmer. Automatically, what happens? Trimmer, the speed will change. Okay, the speed will change means sometimes you may get some small wounds also. And say for example, some equipments are there. Some equipments misbehave. Okay, say for example, your old CRT TVs are there. Now, latest LED TVs, some rectifier unit will be there. So whatever the like voltage or whatever the frequency comes, it will convert into particular whatever the DC system that it will give. Okay, say for example 12 volts or 24 volts, like that supply it will give. But you go back to your previous CRT TV monitors. There, whatever the voltage comes, the same voltage will come. Same voltage, and whatever the frequency will come, the disturbance will be in the CRT TV. You can easily monitor. Say, for example, in the TV monitor itself, if there is some change in the frequency or sudden change in the current, so automatically in your TV, in your old CRT televisions, you'll be come across the disturbance in the TV screen itself. So that is so everything will misbehave. So that condition should not be happen. So what we are doing is we are considering all the unsymmetrical fault happening, that to the symmetrical system, because unsymmetrical fault analysis is very difficult, and we can't. Okay, so what we are doing is we are considering that as symmetrical fault, and we are going for solving the problem. And here, the step number 5, we have to calculate the post-fault bus voltage. The post-fault bus voltage obtained by superimposition of pre-fault bus voltage and the change in the voltage. That is, V bus of fault voltage is equal to V bus naught plus del V bus. V bus naught, the initial bus voltages, plus change in the bus voltages. Okay, that is the del V bus. So now V1F. So what is the fault voltage? V1F, VQF up to VNF. So that is V1 naught. Here VQ F is nothing but VQ naught. Here VNF is equal to VN naught plus here this Z-bus matrix Z11, Z1Q up to Z1N, ZQ1 up to ZQQ up to ZQN. Next ZN1 up to ZNQ up to ZNN. So this is a matrix into this 0 up to minus IF up to 0. So this V so V initial bus plus change in the bus voltage. So change in the bus voltage is the formula Z bus into IF. So that is here. So same thing we have to substitute over here. That's all. So that is V bus F. That is fault bus voltage is equal to V bus F is equal to. So here you need to write V bus F is equal to V1 naught up to Vn naught. Here plus Z bus into this IF. that is a fault, fault current in that particular bus, or bus fault current. Okay, all the buses fault current. So 0 up to minus IF up to 0. So here V1F, what is V1F? V1F is equal to V1 naught minus Z1Q into IF. Why minus means this into this. Okay, so if you just multiply this two, and with if you add in this, so it will come like this. V1F is equal to V1 naught minus Z1 Q into IF. Next, similarly, V2F is equal to V2 naught minus Z2 Q into IF up to VQF is equal to VQ naught minus ZQQ into IF up to VNF is equal to VN naught minus ZNQ into IF. So in general, we can write V1F, VIF is equal to VI naught minus ZIQ into IF. Next, bus voltages during the fault. Bus voltages during the fault, that is substitute the fault current from the equation 1, that is 6.19. So first we saw, we calculated, no? Is that, so fault current is equal to VQ naught divided by ZQQ plus ZF. This IF, we are substituting in this equation. That we are substituting in this equation. If you substitute, then this fault voltage becomes VIF is equal to VI naught minus ZIQ into IF. What is IF? VQ naught divided by ZQQ plus ZF, where I is not is equal to Q. Similarly, VFQ is equal to ZF divided by ZQQ plus ZF into VQ naught. Okay, this is VQF. So VQF, that is this is the so ZIQ is nothing but ZF. So this is the change in the we can tell like I into this VQ naught. Okay, so IF into VQ naught. So that only IF into ZIQ. Okay, so IF into ZIQ. So what is this VQF? VQF is nothing but ZF divided by ZQQ plus ZF into VQ. That is fault voltage. Okay, at the Qth bus. Fault voltage at the Qth bus is equal to this, that is ZF divided by ZQQ plus ZF based on this equation. Based on this equation, same thing. Okay, into VQ naught. That is I is equal to Q. If I is not equal to Q, this is the equation. If I is equal to Q, next VQ naught. VQ naught will be VQ naught will be 0. VQ naught will be 0 in the Qth bus. So that is 0. If the short circuit, if the short circuit is solid or bolted fault, then ZF is equal to 0. Already we have seen what is a bolted fault and a solid fault. So in that condition, ZF, that is a fault impedance, will be 0. Then IF is equal to VQ divided by ZQQ. So this ZF will become 0. So substitute in equation 6.19. So 6.19 shows that IF is equal to VQ naught divided by ZQQ plus ZF. So if it's a short circuit is solid or bolted fault, this, then the ZF is equal to 0. Then this becomes this. So VQ. Next, VQF is also 0. VQF. VQ at the fault current is equal to 0. Next, VIF is equal to VI naught minus ZIQ divided by ZQQ into VQ naught. Because here bolted fault ZF is equal to 0, no, where I is not is equal to Q. For bolted fault, this is the condition. Same equation. Here instead of IF, you need to take 0. That's all. There is no nothing more than this. Next step number 6. Step number 6, what we have to do is we need to calculate the post-fault line current. Post-fault line current. That is from the ith and jth bus. Let us consider the line connecting between the ith and jth bus with a series impedance of Zijs. Zij series. That is Zij series. Let here post-fault line current Ij of F. Ij. That is current between the buses fault current between the buses I and J. That is equal to BIF minus BJF with the whole divided by Zij series. Zij series. With the knowledge of this bus impedance matrix, the fault current and bus voltages during the fault and post-fault line current can be obtained. So for everything, impedance matrix is necessary. For fault current, for we have solved many for calculating the what do you call it, this Newton-Raphson method, line flow analysis, power flow analysis. So for everything, bus impedance matrix is the first step. So first, by closing the eyes, you can solve the bus impedance matrix. After that, you can do fault current, whatever the thing you want to analyze. First, bus impedance matrix is very, very important. So that's what they said. With the knowledge of bus impedance matrix, fault current, bus voltage during the fault, post-fault line current are obtained for any faulted bus. This method is very simple and practical. This kind of method is very simple and practical. Thus, all fault calculation are formulated in the bus frame of the reference bus using the bus impedance matrix Zbus. So we'll see the flow chart. So this sometimes it will be asked in a 10-mark question. So you need to write the algorithm with the flow chart. Sometimes they will ask explain with the flow chart also. It's very simple. So you need to explain all the steps and with the flowchart. Flowcharts, what is the same thing in the flowchart format. First, you need to start the program. Next, read the line data, bus data, fault bus, subtransient reactance of the each machine. That is all generator, everything, or all system, what are all the machines connected. That everything first you need to read the data. Assume the pre-fault line voltage and the shunt elements in transformer, transformer taps. Next, shunt capacitance, series reactance of the lines are neglected. So these are this is the one of the important thing. Assume what we need to do is we need to assume the pre-fault load currents, shunt elements in the transformer, transformer taps, shunt capacitance in the line, series resistance in the lines are to be neglected. So if it is mentioned also, we need to make it to 0. That is all should be neglected. After that, we need to draw the pre-fault per phase network. Pre-fault per phase network by using the positive sequence network and obtain the Zbus matrix using the bus building algorithm. That also bus building algorithm also we have discussed in our previous class. Next, obtain the pre-fault bus voltage from the power flow solution. Obtain the pre-fault bus voltage from the power flow solution. That is V bus naught is equal to V1 naught up to VQ naught up to Vn naught. So pre-fault bus voltage, that is initial bus voltage that we need to calculate. Next, after that, you need to draw the Thevenin equivalent circuit and obtain the fault current. How to obtain the fault current? IF is equal to VQ naught divided by ZQQ plus ZF. That also we have seen. Next, compute the change in the bus voltage by using the network equation. That is del V1 up to del VQ up to del Vn is equal to Z1 up to Z1Q up to Z1N, then ZQ1 up to ZQ2 up to ZQQ up to Qn up to Zn1, ZNQ up to Znn into this fault current, that is 0 up to minus IF up to 0. Next, you need to compute the change in the bus voltage by using the network equation. This also we have seen V1F is equal to V1 naught minus Z1Q into IF up to BQF is equal to BQ naught minus ZQQ into IF. Next, VNF is equal to VN naught minus ZNQ into IF. Then you need to obtain the post-fault line current. What is the post-fault line current? IJF is equal to VIF minus VJF divided by ZIJ series. That is the post-fault currents. Next, you need to print the fault current, post-fault voltages, post-fault line current, etc. And you need to end the algorithm. Okay, so this is the flow chart. So from this flow chart or algorithm, the same algorithm is made in the flow chart. By seeing the flow chart also, you can easily write. So if you just remember this flow chart and the steps, or otherwise first you read the algorithm, this flow chart is nothing because same thing we are just doing in the flow chart form. That's all. So it is one of the important 10-mark question. So in semester examinations, you may accept this kind of questions. That is the obtain the fault current, like fault. This the here obtain the systematic for short circuit computation. Okay, so by using the algorithm, this is the algorithm. How to obtain the systematic short circuit computation. So these are the steps. How many steps are there? There are around 6 steps are there. So you need to draw. You need to write all the 6 steps with the